Welcome students to the video lecture series in online learning. This course is complex analysis with course code MAT 18R4026. This is unit 1.2 offered by the Department of Mathematics of Kalasalingam Academy of Research and Education. Today's topic is power series. So before defining power series, I will be describing what do we mean by an infinite series and its convergence. And with that, I will be also discussing the pointwise and uniform convergence of series, that's basically series of complex variables or series of functions, rather I would say. And finally, I will define what is power series and also illustrate some examples of power series and its convergence scenarios. So first is what we mean by a series. So let me take an highlighter, okay, spotlight, rather I would say. Okay, I've got it. So given a real or complex sequence, an n greater than equal to 1, that simply means this is a sequence of complex numbers. Since we are in the complex domain, we will consider only complex numbers only, but any real number can also be expressed as complex number, as we know. So as of now, I will consider an is a sequence of complex numbers from in like a1 to dot, 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 up to infinity. Now we associate a new sequence Sn of partial sums, which is defined like this. So Sn, how it is defined? Summation of k equal to 1 to n ak. So therefore S1 will be A1, S2 will be equal to A1 plus A2, S3 will be A1 plus A2 plus A3. Similarly, S4 will be A1 plus A2 plus A3 plus A4. This way, we have defined the sequence of partial sums and named it as Sn. The symbol summation k equal to 1 to infinity ak is called a series. Okay, so this is series when we consider the when we consider the sum of all the numbers appears in the sequence. See, there are infinite number of numbers in this sequence, and this notation, that is simply denotes the sum of all the elements of this sequence, is called the series. And this another sequence Sn, this is the sequence of partial sums for this series. Okay, now the series is said to converge or to diverge according as the sequence Sn n greater than equal to 1 is convergent or divergent. So we define this infinite sum to be converge or diverge according when its sequence of partial sums, that is when Sn is convergent, we say the series is convergent, and if Sn diverges, then we will say this series diverges. Okay, further, if Sn n greater than equal to 1 converges to S, the sum or value of the infinite series is said to be S, and we write as S equal to limit n tends to infinity Sn equal to summation k equal to 1 to infinity ak. So in conclusion, I can say that if the sequence of partial sums of the given infinite series converges, then we will say that the infinite sum converges, and it converges to the limit of the sequence of partial sums. That is, if Sn tends to S as n tends to infinity, then the value of this infinite sum or infinite series will be S only. And if Sn diverges, then no value exists, and in this case, we will say that the sequence this infinite series diverges. Okay, Hence, for convergent series, the same symbol is used to denote both the series and its sum. So in future, we will write this symbol only. Okay, whenever we write this symbol, that means this series is convergent. Okay, when there is no ambiguity, if there is some ambiguity, then I have to mention it differently. But in general, this denotes the sum of the series, infinite series, whenever it exists. We call Sn the nth partial sum, as it's defined over here in this equation of the series An, the nth term in the series. Okay. Now, what it says. Now, there is something called uniform convergence. Now, the previous definition was about the series of complex numbers. Now, instead of these numbers, if we write some complex functions, which depends on both the value, both natural number and a complex variable z, then this series will be called a series of functions. Like here, a sequence of function fn converges pointwise to a function f. Okay, so this fn are complex functions, and like f1, f2, f3, these are all dependent functions, and all the functions in this sequence is dependent on the value of n as well as the value of the complex variable z. So this sequence of sequence of functions is said to be converges pointwise to a function f on a set E, and we write it as if n tends to f, if for each z naught in E and epsilon greater than 0, there corresponds an integer n which depends on both the value of epsilon and z naught, for which modulus of fnz minus f of z naught less than epsilon whenever n is greater than equal to this natural number, which depends on both the value of epsilon and z. So in summary, what I can say, since fn is a sequence of complex function for some complex variable z, let us choose a fixed complex number z naught. Then fn z naught will be a sequence of complex numbers. Okay, then that will be no longer for a particular value of z, this sequence will turn out to be a sequence of complex numbers only, and for each z naught in the domain set, if the complex sequence of complex number converges, then we will say that the given sequence of function is converges and converges to the pointwise function f. It's defined for each and every point from the domain set. To say that, this is further, to say that the sequence of functions f of n converges pointwise on a set E is equivalent to saying that the sequence of numbers f and z naught converges for each z naught belongs to E. That's what I was describing. So whenever we will refer that fn is converges pointwise, that simply means for each z naught belongs to E, this sequence of complex number fn z naught n greater than equal to 1 converges. Okay, the limit function f is then defined as limit n tends to infinity fn z naught equal to f of z naught for all z naught belongs to E. Now further, to define the concept of uniform convergence, here we can note that this n is depends on the point at which you are checking the pointwise convergency as well as the positive epsilon. Okay, so n depends on both of these. Now in the case of uniform convergence, this n will be only function of epsilon. So let us see here. The integer n in the definition of pointwise convergence in general vary with points in the set. Okay, as you change the value, as you change the point z dot, the value of n will be changing accordingly. If, however, one integer can be found that works for all such points, the convergence is said to be uniform. Okay, that is what I was saying. If n is only function of epsilon, doesn't depends on the spatial location of the point, then we will say that the convergence is uniform. And in mathematical form, we have to say like this: a sequence of function f of n converges uniformly to f on a set E. Okay, if n converges to f, this double arrow basically refers here uniform convergence. If two each epsilon greater than 0, they are corresponding an integer n which depends on only on epsilon. Okay, no other thing. It depends only on the value of positive epsilon, such that for all z belongs to G, this is very important, for all z belongs to E, this modulus of f1 f of fn of z minus f of z always less than epsilon whenever n is greater than this n. Okay, this is the natural number. N depends on epsilon only. Thus, when n is large, fnz is required to be uniformly close to fz on E. Okay, that's what we mean by convergency, both uniform and pointwise. Now, let us see some examples. Okay, just see it here. Okay, example, let us choose f of n to be 1 by nz. Then we see that the sequence fnz converges pointwise but not uniformly to the function f of z equal to 0 on the set 0 less than mod z less than 1. That is, the domain is here the unit circle, and it's exclude the boundary circle and also exclude the origin. Okay, for a given epsilon greater than 0, in order that in order to maintain this modulus of fnz minus 0, that is equal to 1 by nz, this has to be less than epsilon according to the definition. Now, this is less than epsilon only when n satisfies this condition, that is n greater than 1 by epsilon into modulus of z. So corresponding n, as you can see, corresponding n is depends on both z and epsilon, is an integer greater than 1 by epsilon into modulus of z. Note that as z decreases, the corresponding n increases without bound, that we can see. Okay, as modulus of z decreases, then the value of this n basically increases, it changes, it's not fixed for all z. As you will be changing z, this value of n will be changing. Thus, we say that the sequence converges pointwise, but not uniformly on this disk, on this unit disk. Okay, so this is one way of showing this function is only pointwise convergent, not uniformly. However, I have considered a second example which defined this way: f nz equal to 1 by 1 plus nz. Then the sequence of function f1z converges uniformly in the region whenever modulus of z is greater than equal to 2, but does not converges uniformly in the region mod z less or equal to 2. Indeed, the sequence fn converges pointwise everywhere to the function fz equal to 0 when z not equal to 0 and 1 if z equal to 0. Now, if modulus of z is greater than 0, what will happen? Modulus of fnz is nothing but equal to modulus of 1 by n plus z according to the definition. This must be less or equal to 1 by mod of nz minus 1. Now, maximum modulus of z is always less or equal to 2. That's why this must be less or equal to 1 by 2n minus 1. And hence, since we are increasing, we are decreasing the denominator, the fraction will be increased, so that will be less or equal to 1 by n. So what we can see that modulus of fnz is always less than 1 by n, and in this expression there is no function of the variable z. So it's always, therefore modulus of f1 z less than epsilon whenever n is greater than epsilon. So this natural number, this condition is not depends upon the complex variable z. So which proves uniform convergence in the region mod z greater than equal to 2 for this function fnz equal to 1 by 1 plus nz. However, if we change the domain to be modulus of z equal less or equal to 2, then it is not converges uniformly, as we can see here. Okay, from this example. Okay, and if we change the domain, then we are getting the uniform convergence. So this example also shows that the uniform convergency of a sequence of complex functions also depends upon the domain of definition. Okay, domain of the definition of the sequences. Okay, this domain is important. Now I will be defining something called Maclaurin's and Taylor series. So unfortunately, knowing that an arbitrary series summation n equal to 1 to infinity fn converges or diverges at some point z equal to z naught gives no information about the series at other points. Suppose you know this series is converges at some point z naught. With this information, you cannot say that whether it will be converges or diverges at some other point on the complex plane. Suppose I am choosing some other z whose modulus is less than z naught. But with this condition, there is no clue that whether at this point this series will converge or not. However, we can specialize the sequence f and z. So if we consider a particular form of this fn of z to obtain a class of function for which the behavior at a point always determine properties in a region. Okay, this class will play an important role in the theory of analytic function. Okay, so what it's saying that I will be, or we will be considering a special form of fn of z. Okay, and for this special form, the convergency or divergency of a series of complex function will be on the base of the region at which it is converges or diverges. Okay, so let us check or take this class of functions. F n z is like this form: a n into z minus b whole to the power n, where a n and b are complex constants. Then the resultant expression, I mean the resultant expression of the previous this infinite series will be like a naught plus summation n equal to 1 to infinity a n z minus b whole to the power n. Concluding, we can write it as summation n equal to 0 to infinity a n z minus b whole to the power n. And this kind of infinite series is particularly known as the famous power series in z minus b. When b equal to 0, this series takes this form, simply summation n equal to 0 to infinity a n z to the power n. So this is how we define power series. Okay, at around origin, and this is power series around b. Okay, this is a power series in z only, and this is a power series in z minus b. This way also we can say this is a power series in z minus b, and this is a power series in z. Our efforts will be focused on properties of power series defined by this. Upon subtracting z minus b for z, it becomes a simpler matter to translate this properties to those of series defined by 6.12. Here, we state and prove some result providing the qualitative behavior of the conversion of the power series. So I will be discussing only some examples. I have omitted the proofs for simplicity. Okay, proofs can be found in any book, any standard book in our reference. So this theorem plays a central role in the theory of power series. So what it states? It states that to every power series, summation n equal to 0 to infinity a n z to the power n, there corresponds an real number capital R, which is finite, or sometimes it may be infinite also. Its ranges lies from 0 to infinity, and this equality is also there. So it may be 0 or it may be infinite also. So infinite means the whole plane basically. You will get to know this, for which the series converges absurdly in modulo less than R if 0 less than R less than equal to infinity. Converges uniformly in modulo less or equal to R less than R if 0 less or equal to R less than infinity. And diverges for all modulo greater than R whenever R is in this range. So what it says that for any power series there is a real number R, and this power series converges whenever this mod j is less than R and diverges whenever mod j is greater than R, and this R is called the radius of convergence, or in short we sometimes say it like ROC, ROC, that simply means radius of convergence. So with this example, I will be describing 2 or 3 examples, and rest are left for you for your consideration. So the series, this Zn by n, just to the power n by n, definitely it's a power series in Z. We can see that this converges at -1 and diverges at z equal to 1. Therefore, its radius of convergence must be R equal to 1. Since it converges at z equal to -1, therefore for all mod z less or equal to 1, it has to converge. That's why it is R, and it also diverges for all mod z greater than equal to R, since it also diverges at z equal to 1. So this way there are several examples. You can take it and you have to find out from the region where it converges and where it diverges. If it converges somewhere, then you consider a circle with that modulus, and in this circle the power series must converges. And if it diverges somewhere, again you can consider a circle with modulus of that point, and the power series will be diverges everywhere outside of that circle. So that's the theory. So with that, I conclude today's session, and please follow the next session. Thank you, students.